So, welcome back. Our next speaker is Professor Sumitendra Majumdar. He is a professor in Department of Physics, University of Arizona, and his expertise is strongly correlated systems. And he has immensely contributed in the field of strongly correlated systems, especially in the conjugated uh, electronic properties of conjugate systems and also superconductivity. That's what he's going to talk about today, and he'll be giving a flavor of the development of superconductivity theory with that, please.
Oh, thank you, Manoj. Do I need a mic? Of course. Oh, yes, that's true. Yes. Okay, I've been sitting here for the last 2 days, suffering from what is called imposter syndrome, because I'm not part of this workshop, but I have connections to this campus since 2005. I've known Dr. Sadhas Gupta for a long time, for quite a while, Dr. Kumar, and I wrote to them, I'll be in India, can I be given an office as usual? And they said, we'll give you an office if you give a talk, or something like that. So anyway, the reason I say that is because this talk is going to be hard. I'm not going to pretend it's easy. It's a very hard talk because it combines a whole bunch of different concepts, and I'm not a computational person. The computational person are these people. Many people know this person. He has spent time at the SN Bose as part of our Indo-US research grant that just over. As part of an Indo-US research grant. So I'm going to say very, very little about computations, and then I'm going to go here directly. This is going to be a fast-paced talk, unfortunately, because as I said, I was not part of this workshop. So why is this question difficult? Because it already assumes that the audience knows a lot about cubeglets. I understand that's not true for students. It assumes that there is a problem, and I have to prove that. And anyone who is asking this question is going to say, what is the new theory? So it is at least 3 talks, which I'm condensing into one. And so that's going to be difficult. But there are some references, and there is a talk of mine on the SN Bose Institute's website. I'd given a talk over online talk. So that gives the background, and that's much slower. That talk is 1/3 of this talk. All right. So let's go. So here is a question I want to ask. Look at the history of coordinated electron superconductivity, organic solids, tetramethyl, tetraselena, BEDT, TTF, etc. Heavy fermion superconductivity, which is still an interesting subject. Cuplet was 87, fluoride is 1991. So I would like to start this talk with the following hypothesis. Making progress is no good. We would like to have a solution. I got my PhD at this point. I'm 70 years old. When are we going to solve the problem? So obviously that involves a certain amount of immodesty. But we have to be there because otherwise we keep on making progress for the next 50 years. That's not acceptable. So what is the theme of presentation? I'm going to claim that there are many ideas in electronic structure concepts that have existed over the years, but they have appeared in different fields. So if you do DFT, most of the time you get mixed valence. But there are possibilities to have integer valence where the charge is 1 or 0. Of course, 1 is not 1, it's 0.8. 0 is not 0, it's 0.2. I'm going to talk about some phase transition that I'm pretty sure, with the exception of Ramasesha, probably no one has heard of. But that is a transition between 2 integer valences. The same thing was proposed around the same time in heavy fermions, but these people are not aware of these people. And then I'm going to talk about negative charge transfer, which was barely touched upon in the talk, which was very entertaining and very enjoyable, but somewhat incomplete because he was a tutorial of Dipankar Dasar. I'm going to come here where Dr. Sadhas Gupta has done some work, and I'm going to claim that you can have a global picture and you can tie this down. So these are the 2 papers. This is a strontium glutamate, this is cuprets, and I'm going to tie this around. So obviously you can see that there are multiple talks here. So that is why it is fast-paced. So let's go back to 1981, the first neutron ionic transition. This guy was a genius. He was an experimentalist who taught me more theory than anyone. He was not my instructor. I met him at conferences. These are charge transfer complexes, layered books, molecules were arranged like books, donor, acceptor, etc. And they can have charge if you can read this donor 0, acceptor 0, or donor plus, acceptor minus. He looked at the charge transfer absorption from donor to acceptor, and everything here is ionic, B plus A minus, everything here is D0 is. So after plotting this, he said, if I do some fun things, with temperature or pressure, I can have jumps from D0, A0 to D plus A minus, and he showed that, and many people, including John Hubbard himself, collaborated with him to give the theory. This is completely different. Helifornions. What I'm plotting from this extremely famous paper, it was a brief report which became extremely famous, probably a PRN reject. This is the probability of having ytterbium in the valence 3 plus, and this is the valence 2 plus, and the integer valence jump is occurring as 1 over t. This is an experimental plot. So these two are unrelated. There is no overlap between this field and this field, but they're actually the same phenomenon. All right, so I want to now draw attention, if you can read here, one thing that is not or very rarely recognized in the field of oxides, the second electron affinity of oxygen from oxygen to oxygen 1 minus is negative. You get it easily. It does not accept the second electron. The energy you have to put in is 8 keV. So there are compounds which are called negative CT. I'm going to come back to that, in which oxygen is known to be fractionally charged. Two oxygens together have charge 1.5. And that 1.5 is a magic number that I'm going to come to. Barium bismuth oxide, for example, for 30 years, this was believed this was bismuth 3 plus and 5 plus. No, it is only 3 plus, which means some of the oxygens are 1 minus. I'm going to come to that. Okay, I jump topic now. So I'm already 3 minutes behind, if you think this is fast paced. Band theory has actually, without using those words, Dipankar Das Sharma pointed out that if you have an odd number of electrons per unit cell, the system is a metal. From the 1950s, people have known this is not true, because look at the electron numbers. Doesn't matter how the electrons are distributed, the total is odd, and the system is a semiconductor. So something is missing. The answer is that I have to go to interacting electrons theory. So the theory is actually quite easy. People have already introduced creation and annihilation operators. I have two sites, both containing 1 electron. These are creation and annihilation operators. I'm moving an electron from I to J, J to I. I'll create a double occupancy. Every time I have 2 electrons on the same site, they don't like each other, repulsive interaction, that will give me an antiferromagnetic semiconductor. So that's the Howard model. What happens if I have 1 dimension? The solution today, we heard many talks on singlets. You get a singlet in 2 dimension. Actually, this is preferred over this because of the number of neighbors, which is larger. In 2 dimension antiferromagnetism. In 1 dimension, these are 2, it's a plus. It's a bunch of singlets here, a bunch of singlets on the other one. I have singlets between 1, 2, 3, 4, 5, 6, or 2, 3, 4, 5, etc. So that's what this is. Okay, this is all known. Now I'm jumping into cuprate. Okay. Don't hesitate to ask questions, even if I'm going fast. I will slow down at a certain point. So this is what lanthanide strontium copper oxide. That's this side of the phase diagram. Here it's an antiferromagnet. That's why people think it's a Howard model. And you dope it, means you put in a few strontiums. The antiferromagnetism disappears. There is a phase that no one understands, even after 30, 40 years. That's called the pseudo-gap state. Inside this, there is some CO, etc. Let me not go there, but you get superconductivity. On the electron dope side, it stays antiferromagnet for a very long time. That's already a challenge, and superconductivity is over a very narrow concentration. The antiferromagnetism is because of the copper holes. Copper is believed to be 2 plus. Then it is 3d9. 9 electrons means 1 hole. So that's the spin of the hole. The Hamiltonian, in terms of Howard model, is written in terms of the holes, not electrons. Okay, so it's a large U Howard model. It's appropriate for this point. Let's go. So this is now old. I'm going to talk about spin, not going to talk about spin fluctuation, just slightly different from RBB. What Phil Anderson said, that remember we had those pictures of singlets as opposed to antiferromagnets. So that's a singlet. So what Anderson said, that of course it's an antiferromagnet when I have every site occupied, but if I create some doping, some vacancies, I will create these singlets, and in 2 dimensions you can have an infinite number of singlets with the same diagonal energy. So you have a state which basically has configurations with the same energy. You put a field, it will go from one to the other, the wave functions remains unchanged, and that's a superconductor. I don't have time to talk about spin fluctuation because it's the same Hubbard model, but it's not RBB theory. It just treats, some people have talked about magnons, spin excitations are like phonons gapless, except that it goes as k squared instead of k. So, but the idea is that the electrons coupled to their own spin excitations, which is like double counting, I think. But without going into that, claim was that if in the square that is Hubbard model, I generate a few holes and get a superconductor. I have here 30 years. This is now 35 years. There's been no evidence for superconductivity within this model. I'm going to get into that later. What do I think I need? What do we need to prove superconductivity? I understand not, superconductivity is hidden under so much of math. It actually looks quite scary. You can spend some time understanding it, and there is no reason to be scared of, because the actual physics is very simple. Because there was a lot of discussion about what happens if I have dimerization in exactly half field band. But if I remove some of that and the state dimerized, if I have a collective state in which the singlets move, that's a superconductor. That's it. So what do I need to do? I need to prove that if I destroy a pair on these two sites and I create them on two distant sites, and there is a certain distance between them, and I plot the probability of destroying the pair here and creating somewhere, and I increase the distance, as I go to infinite distance, it still stays non-zero. That's called long-range order. If I have that, I have a superconductor. That means charge motion is occurring due to singlets. And I should have long-range order. And the other requirement is, if I calculate this at u equals to 0, if I calculate this at u non-zero, the u non-zero value of the correlation function must be larger. If I satisfy these two, the system may be a superconductor. These are necessary but not sufficient, but these are necessary conditions. Okay? All right. So I give only a subset of papers that have looked at this numerically over the years. It's not terribly biased. It's actually, I have removed our own papers from here, but there has been no direct computation. This workshop is about computations. No computation finds superconductivity in the weakly doped Hubbard model. Okay, I'm going to spend a little bit of time on this. That's why I have it on red. Same paper. These are the references. Seven by Imada, but Imada has been on all sides. This S sum will also appear here, and here I will take a breather. Any questions? Or let me actually go to the next slide. I was supposed to be here at 8 minutes, 45, 19. I'm here at 11 minutes. All right. This paper has dramatically changed the field, although there were indications that there was something wrong with the superconductivity within Hubbard model picture. Anyway, why has this paper been so influential? Because 1, 2, 3, these are all who's who in the field of DMRG and quantum Monte Carlo. What I am showing, so this is direct quote from the abstract. This is the abstract. Okay, you can read it while I'm shouting or sleeping or whatever. They put an external field which will tend to create pairing. And then, if you are superconducting, so the blue one is the superconducting one. The red one is something called stripes. I'm not going to get there. They're supposed to be competing. What you want to see is that as you lower the external field, that creates pairing, whatever that is, the superconductivity has to win. And actually, DMRG, QMC, in both cases, it loses. So that's just one set of results that these people, they compared the data by two different things and they said absence of superconductivity, and no one argues about this anymore. That doesn't mean that people have given up on finding superconductivity to two-dimensional, because one of the things is they pick a square lattice, but you can put a diagonal T prime and etc. and keep trying this. And results are controversial there. I'm not going to go there. I think they will find nothing. That's a different story. All right. So this is 2020. Within days of this appearing, it acquired many citations because the paper was already known thanks to archive. So let's now proceed. If that is true, why is it for such a long time people have been focused on the Hubble? Why do we do that? I think the day I came, somebody was talking about ladders. So this started with this question. Because two-dimension is difficult, we talked about sign problems and etc. Is it possible that we can talk about superconductivity in something simpler? So something which has been tried out since 1992 is a ladder. So you have a copper side everywhere. It could be copper or any spin one has. And the first paper, I want to forget all this. Look at the date. It's going to come in my talk. In 1992, these people proved that there is superconductivity in ladders. And I'm going to now slow down and explain that, because this is what has driven to a large extent the idea that there is something in the Hubble bond. Okay, so this was part, by the way, the talk of mine that's on the, or was on SN Bose's website. So let's go slow down. The best paper is actually this one. One wants to know this. This is the best paper. That's according to me. It is very easily understood. But you can see that some people are still pushing that idea. Kivelson has a PRL 2021 or 2022 with the same idea. Not going to spend too much time on that. So what happens if I have a ladder? So it could be J for 20, and it could be Hubble model, but it's an exactly half filled with every site occupied by a spin. It turns out that because there are only one and one neighbor here, it doesn't matter how weak this is, you will form spin singlets here, not antiferromagnet. Remember, singlet is different, up, down, minus, down, up. There are some very famous papers. This paper has thousands of citations with Dagoto and T.M. Rice. What they're doing, I will move out. This is J perpendicular is J prime is this one. It doesn't matter how small this is. The delta speed is non-zero. It goes to zero this way. For the smallest J prime, there is a spin gap. Why is there a spin gap? Because the singlet has to go to a triplet. There is always a gap. So this paper is quite famous. If you do this, you are always going to get a singlet. These are paired. So what does that have to do with superconductivity? It's very easy that if I create dope now, if they're far from each other, I've destroyed two singlets. But if I've destroyed it here, I've destroyed only one singlet. So it is preferable to destroy them here. And then, of course, these singlets will move. This one moves here. Somebody talked about triplons. This is somewhat similar to triplons, except the system is non-half filled and it's a conductor. So the conductivity is due to spin singlets, and you should get superconductivity. Is that true? Okay. Let me jump down. It turns out that actually, I don't know if I have slide for the calculations. Yes. Okay. So in parallel, there is a real material of this composition. When it starts with strontium 14, that's a semiconductor. You replace some of the strontium with calcium, same valency, but size is different. If you go to calcium 11, it actually becomes a superconductor. What's the structure? These are layered structures. This is important. Now it becomes serious, even though it is fast-paced. So these are chains that look like this. And here you have ladders. You can see the ladders here, something that I'll come back to. This is the ladder, and you can see the next ladder is coupled by a 90-degree copper oxygen copper. That copper bond is extremely weak, and the system is almost quasi one-dimensional. Why is it extremely weak? Because oxygen, this is px and this is py orbital. This px hole cannot go into the py, and so this coupling is almost zero. So that's called a telephone number compound. It's believed that if you calculate the number of holes, assuming copper is 2 plus, then there are 6 holes per formula unit. This is the one formula unit. You can do all kinds of things and come to the conclusion that between 4 and 5 are on chains, between 1 and 2 are on ladders. There's not much disagreement about that today, even though there was in the 1990s. All right. So why do I mention this? Remember, we talked about pair-pair correlation. What you have to do is you have to create a singlet on one of the rungs. One is leg 1, 2 is leg 2 on rung number I. That's the creation of a singlet operator on rung I. And then you destroy the singlet on rung J, created on I, and you calculate that correlation function as a function of distance. Okay? Let me know if you don't understand what is being calculated. I will do calculations. Actually, I do. All right. So this ladder is an example of what is called Luther-Emery liquid, the literature on which goes back to 1976. This system will be either charge order, and I've not explained that, but you saw in the phase diagram there was something called CO. It's either the charge has periodic arrangement or it will have superconducting correlations. This is what we are calculating. We want to see how PR goes as a function of R. Does it actually stay finite at infinite distance? But this is quasi one-dimensional. This is a theorem. You can't have a true long-range order here. It has to only decay slower than alpha less than 1. It has to decay slower than r to the minus 1. So if you do that, then people did calculations, and they actually found that, so k is 1 over alpha. So alpha has to be less than 1, k has to be larger than 1, which is what people found. All these papers, extremely famous, theory correctly predicted ladder superconductivity because this experiment, determination of superconductivity, came in 1996. It's very, very rare that the theory comes before. This was a great triumph of the idea of the ladder theory. Our model gives superconductivity. Yes.
Sorry. Why this? I mean, alpha is the true companies.
If it's less than 1, it decays slower than all other correlation functions. The system has a choice of being charge ordered or paired. If it is slower than r to the minus 1, then the pairing correlation wins. Okay? It will not have true long range order. That's called a quasi long range order in this thing. So what? Yes.
It means that if we connect the several quasi-long several quasi-1D chain, like to make a three-dimensional system, then we may have the
Right.
long range.
Right. If there is some interaction between the ladders, then we will get true long range order. Because the real system is three-dimensional. Yes, thank you. All right, so that's the calculation. Beautiful thing, and I have it in quotes because this has been repeatedly, even today, it's said that that was so wonderful theory predicted 1992 versus 1996. Okay, so this is my claim to being part of the DMRG group, but I don't know anything about this slide. It's my collaborator, Thorsten Clay. Trust me, he knows quantum Monte Carlo, exact diagonalization, DMRG, everything. I think Ramasesha will give him that certificate. He knows all the calculations. He's very precise. All right. So we asked this question. From 1992 to 2020, everybody is doing calculations with just the copper sites. But go back to the real ladder, and there are oxygens. This is something amazing. to me that for 30 years, no one asked what happens in the real data if I put the oxygens. A natural question to ask, right? I don't know if I will have time to go to a slide which told me that this will fail. This was not a trial and error calculation. I will not have the time, but this is day marching workshops. I'll just show the results. So what we did, oops, what happened? Okay. So what we did is we put in the oxygens, we put in TPP, BP, etc. This is the Hamiltonian. I'm not going to spend time on this. This is the site energy difference, the delta, the charge transfer gap that was there without using a Hamiltonian in Dasaga stop. There is hopping between T and P orbitals in this direction, hopping in this direction. There is a TTP and there is UD, UP, etc. Now, all these parameters are calculated by other people. We don't want to take, so more or less there is some convergence. What these parameters are is that they are materials. So we took them, and this is again our claim to whatever. So we took them from a paper by Imada. So Imada has multiple papers after this also. And then we calculated the spin gap. I'm not going to spend time on this, but how long do I have now? I'm actually going quite fast. 3:45, half an hour. Half an hour more. Let me slow down. So,
Can be fast.
sorry?
It can be fast.
So, it's nice, it's already very fast. Okay. So, what we did was, remember, if I go back to this picture, the reason we have superconductivity is because, is if I have these here, then there are singlets here. So the system still has a spin gap. It is because it has a spin gap, they move like this. So the spin gap and superconductivity are related. This is also true within the BCS theory. You can't have one without the other. It's also true in BCS theory. So one of the things people calculate is spin gap, and which we did for our three-band model. I'm not going to spend time on this. I'm going to claim that if you look carefully, this is the undoped. Spin gap is very large, but larger the spin gap in the undoped, smaller it is in the doped. The changing parameters. So these parameters are all from Imada. So this is something interesting. Yes.
Actually, your model didn't have UPD, which is supposed to be really the crucial one. If you have UPD, will the qualitative nature remain same?
It will, the superconductivity will disappear even faster. Okay, if I have time, I'll show you the physical picture. It will disappear even faster. There is a very strong physical reason. So one of the things that have UPD, of course, just renormalizes the spin gap. First of all, it will just quantitatively change the spin gap without doing anything.
But the doping effect will be even stronger.
Yes. So there are various parameters we work with. We work with TPP0. So oxygen hopping, TPP 0.5, etc. Without going into details, basically TPP increases the spin gap here, but decreases the spin gap here. The UP, U on oxygen, decreases the spin gap here, decreases the spin gap here. Both UP and TPP severely diminishes the spin gap here. So what does it do with the pair-pair correlations? This is just to show that we did a real calculation. Don't bother in this. We'll go to the next slide. So essentially, this is our unit. This is Imada's use of B. When I say L equals to 96, that is 96 times 5. Because that's the number of rounds. So 96 times 5 is quite large. That's the largest three-band model ever tried. So these are not small sizes. There are people in DMRG who use this M. The M, if you look up DMRG calculations, I have no clue what that is, but that's usually 5 to 7,000. Ours is 19,000. You cannot do better than this. Take my word for it. This is Torsten play. And we find, remember, alpha has to be less than 1 or to be minus alpha. Alpha has to be less than 1 to have Poisson-Normal in order. For arbitrary realistic parameters, alpha is greater than 1. So that's the result. This is different doping. And this is, of course, not realistic. You can get alpha less than 1, but this is the realistic set of parameters. Alpha becomes greater than 1. So we said that there is no quasi-one-dimensional Luther-Emery superconductivity. For all, this is not archived, this is appeared in PhysLab. So there was intense objection to this paper because they said, oh, data are not interesting anymore. Not true. As I said, data papers are still appearing, and I'll come to that. But essentially, once you put in the oxygens, the pairing disappears. It seems I have time to explain this. So we actually calculated a whole bunch of other pairing correlations. The one that I showed was this one. But we calculated many other pairing correlations. I'm not going to go into defining them. These are the only ones you can have. Either the R dependence is as fast as this, so in the sense that alpha is greater than 1, or it is even faster. Okay? So some of these are even faster. There is no case where we found alpha less than 1 for realistic parameters. Now, because I do have time, and I do want to impress upon people the importance of thinking in configuration space. Because one of the things that has happened in this field that people talk about density of states, bands, etc., etc. There is an alternate way of thinking in configuration space, which is the real valence bond theory that goes back to Linus Pauling. So let me see if I can convince you why they thought this would happen. You see, when I have just the coppers, the spin singlets are sitting on this. It is known that within this Hamiltonian, when I dope this, the extra holes go here. So the absence of singlets, which is the mirror image of the singlet, it's actually over this very large H-shaped 1, 2, 3, 4, 5, 6, 7 atoms. Everybody knows to move some excitation from 7 atoms to the next 7 atoms, you have an effective mass that is very large. That already tells you something might happen if my singlet is spread out over this H, that we might use the pairing. Now, the pairing is lost faster as I put it TPP. Why is that? Because if my holes are spread out here, and if I introduce this hopping, that's a pair breaking term. I am taking this oxygen here. So once I introduce the oxygen-oxygen hopping, that's a pair destructive term which was not there in my one-band model. In other words, we suspected before we did the calculation that if you do this, the pairing is going to disappear, and it does. Anyway.
But just a second. The two are orthogonal, so where is the transfer integral? The two arguments are orthogonal. So where is the transfer integral?
The transfer integral is still there in TPP. Ask Imada. Everybody agrees on that. It's just the sign. Oh, right next to you. It's not a TPP. Just we are in a straight line.
So
that's actually a PP pi interaction. It's there. So what he has plotted is actually P sigma,
Yes.
but there is always a P pi, and it is PP pi.
Yes.
so I think Slater constant parameters will give you.
Yeah, of course.
Yes.
He has shown only one P of it.
Yes.
He has not shown the other P of it.
So we actually consulted those papers, but that was way back. We took the parameters of Imada. We just are doing the Imada parameters.
But that, in other words, if you introduce TPP, annualized singlet picture actually breaks.
Yes, I agree. I completely agree. And that's exactly why our singlet gap was decreasing so fast. So there are two different things. One is that the mass is very large. You have to move the entire thing. This moves here, this moves, etc. And then there the pair break.
Can you just, how will you have this H? Can you just?
Oh, I created it.
No, but can you just?
Oh, so you have spins here. but they are distributed here already. If you have oxygen, if you take the real parameters, this spin is 0.75 here and 0.25 here. Now, with those parameters and experimentally also, the holes go into the oxygen. So once you put in the holes, there is a lot of population here. Okay, so it's not even surprising.
Yes, Sumita, one silly question. So, how did you compute it? I mean, like this Hamilton, it's copper have the holes and oxygen have the electrons.
No, oxygen also has holes.
Holes. So
Yeah.
everything is holes.
Everything is holes.
So in this case, you have this like a.
So oxygen 2 minus is oxygen hole population 0.
Once you have this big side, I don't know how easy it will be to convert into this.
I don't convert anything.
Singlet picture because.
No. The singlet pictures are this. So we have the same parameters, same creation operator that the one that people had for this one. But then you can do it with this, and then you can have it on all the coppers. You can define singlets any way you want. So the holes are here.
Now you'll have many overlapping singlet
Yes.
formations.
Yes.
So it will be yellow like.
Over this sides.
Yeah.
And this one is the H. This one is the real one. In every case, so this one, for example, the parallel correlation decays very fast. Okay. All right. So, summary and conclusion one, that this is the only case where superconductivity over our model is found and understood. This does not carry over to the real material. Theory for cuprates need to move beyond one band models. I'm going to come back to this. So we had a lot of fight with Pierre and gave up very quickly because of what I'm going to show next. So let's go to this material again. This is chain, this is ladder. Supposedly, we're getting superconductivity from this system. What's the actual experiment, which not a single theory paper has talked about, whereas the experimentalists continuously talked about this, and I knew this because if I reveal it now, there is a review paper in Physics Reports I was referring, and that was 2006. The actual experiments are shown here, and I'm going to slow down considerably. This, the interladder direction is A. This direction is C. The separation between the layers is B. In the experiment, what you do in the layered materials, you put in holes. In the experiment in the ladders, you put pressure in the B direction. So these come slightly close to each other, but up to 9.6 gigapascal, there is no change in the ladder structure. Something to keep in mind, 9.6 gigapascal. So this is the resistance in the C direction. So that's the leg direction. And you can see at ambient pressure, it's actually semiconducting, it goes up. To quick apply pressure, only at 3.5 gigapascal, it becomes superconducting. In the wrong direction, it's even worse. It doesn't come down at all with temperature. It goes up right away. It's sort of incoherent resistance right from the get-go. And you apply pressure, it does do this. You take that resistance in the A direction over C direction, it actually at ambient pressure increases enormously. So the resistance in the A direction is increasing enormously over C by a factor of 80. You put pressure, it cuts down. So the superconductivity is under pressure. You take the geometric mean, it's a standard practice in anisotropic materials, rho C times rho A. Take the square root of that and you plot a resistance. This line that you see is H over 4D square. This is the resistivity here to convert it. H over 4D square is the universal two-dimensional resistance. The system is two-dimensional just before it undergoes superconductivity. It tells you already it may have nothing to do with the ladder theories. You read these review papers. Now, this is the PRL, this is the review paper. There are other papers. Experimentalists have consistently said that maybe our observation has nothing to do with the ladder theories. Nobody cared because we need to find superconductivity. All these things, negative things, not accepted. But this one explicitly says this is a one paragraph that maybe it has nothing to do with superconductivity. I mean, with the ladder theories. So
You said the structure doesn't change.
structure doesn't change up to 9.6
So
gigapascal.
the two-dimensionality is associated with what? An increased overlap?
Sorry,
The two-dimension, the system going two-dimensional, what is it associated with? An increased coupling or?
I am going to explain that.
Oh, okay.
And I'm saying there is only one explanation.
Okay.
Not only I'll explain that, I will explain there is only one explanation. Okay? All right. This is something else which also appeared in parallel. Remember, the appearance of the superconductivity was 96. 1 year before that, a French group, this group is very well known in the field of organic superconductors. Denis Jerome, who discovered TNTSF, etc. They did NMR measurement under pressure. This is science. So you can see this is atmospheric pressure. This is night shift. They're measuring the spin gap. The spin gap goes to 0. Sorry, the night shift, the spin susceptibility shows this figure. That means the spin susceptibility goes to 0 because there is a spin gap. If I have a triplet singlet gap, to get the susceptibility, I have to excite it, otherwise the susceptibility is 0. Sure enough, ladder theory works. But at the pressure where it becomes superconducting, the gap is non-zero. They wrote it and they said the same thing, that maybe this has got nothing to do with ladder theories. Ignore. This is far more interesting in this paper by Fujiwara. They had written a paper in 2003, but by the time 2009 came, everybody accepted ladder theories are already okay. This is far more interesting. What they are doing, let me skip this one. They are looking at the spin gap as a function of pressure. It is almost constant, but something drastic happens. And that's exactly where almost the superconductivity appears at reaches maximum. This is a phase transition, which may be related to this. And these people pointed out, I don't have time to get into that, that this behavior is very much like phase transitions in the opposite direction that are seen in the layered materials when you do with zinc substitution. Superconductivity disappears right away and the resistance is the same. So it seems that there is a universal mechanism of two-dimensional semiconductor to superconductor transition. There are lots of other literature stuff I can't get into, but this is a very interesting thought. If I had time, I would explain this exactly to do with this. I mean, the expression for the magnetic susceptibility, two different quantities, and the third quantity, they're all occurring at the same place. It's a clear indication of something drastic going on. It's not something just some crossover. All right, so we ask this question, that how can I measure the dimensionality of resistivity? I cannot measure resistivity, so I'll calculate bond orders or charge transfers within our Hamiltonian for coupled ladders. So this is bond order between copper and oxygen along the length, the C direction. This is intra, which means the intra bond order is this one. Okay, that oxygen. And then the strength of interladder, which is the interladder oxygen. So this oxygen, because copper is 0. So we'll calculate this hopping, bond order, this bond order, this bond order, and also this bond order. And see whether we can, what parameter changes the interladder bond order with respect to the intra. So this is right now in the preprint state. This is for this dp prime. There are two values they have chosen to show this has got nothing to do with dp prime. The interladder oxygen hopping is flat with respect to doping. Why are we plotting it as doping? Some of the experimentalists said that maybe when I put, and that is related to your question, Dr. Manohar, that when I bring the layers closer together, maybe there is transfer of holes from the chains to the planes. So that's delta. And as a result, the dimensionality increases. So we plot from the 0.0625 to 0.25, it is flat. This is the interladder. The dimensionality does not change. If anything, the effective dimensionality, this divided by this, decreases. The anisotropy increases, and the Kojima reference actually experimentally did magnetic stability, and they said the anisotropy might increase the entropy. And that's exactly what we find. So this is not it. This is not doing the dimensionality transition. This is on the paper, you can see this is almost flat and doesn't work. So now comes the hard part. This is where I will go way beyond band theory. Let me say that I have a metal oxide in which the metal can exist in two different zero states. I already showed you chromium oxide is a metal, the oxidation is 1.5, people know this, FeO2, etc. I'm going to come back to this. But I'll give that is called, okay. If the system is here, it's negative charge transfer gap because the absorption is such that it will take me from here to here. This is what everybody assumes. This is the ground state, this is the excited state. So let us compare those. It's very useful if one did a BSc in chemistry, which is looked again. And what determines the relative energies of this? What I'm going to claim is that for 30 years, when people write down Hamiltonians, they take this delta dP to be a constant. They calculate it for semiconductors and they use it for conductors. But this is not a constant because this is a sum over many terms. I'm not the first one to say that. One can go back to neutral ionic transition and find it in the work of John Hubbard himself. One can go back to various stability in heavy fermions and find that equation that I'm going to show in a slightly different language in the Ytterbium, etc. But those are two different fields. Nobody is looking at them together. So why is that delta dP doping dependent or pressure dependent? What is the difference between these two? In is the ionization energy from n-1 to this. Electron affinity of oxygen is this. Electron affinity is always negative until I go to the second charge. It's actually positive. Maximum energy difference is I will get some Qi Qj over R square over this. I'll get the Qi Qj over R square over this. That is the difference. Let me ignore this for the moment. So, when will I get discrete integer valences? When these many body terms are far larger than the hopping integral. That's a condition for getting integer valences. So basically, I don't have the equation. Okay, so let me write down the equation. I'm adding the ionization energy for going from copper to 1 plus to 2 plus, adding the electron affinity for going from oxygen 1 minus to 2 minus. I'm putting the gaining Medlock energy that I would get for the higher charge and gaining Medlock energy related to neutral that I'll get from monocharge of the copper. So because these two terms both prefer copper and copper plus oxygen 1 minus, why is the semiconductor copper 2 plus? Because this term is negative. Larger charge will give larger Medlock energy, it goes over. But you can see that the site energy difference consists of these three. Now think of this configuration, the copper 1 plus, where I have a few extra holes. Not only this term will change, my gain in Medlock energy for higher charges becomes smaller because some of the charges are already smaller, oxygen 1 minus. And then I have to add another term because if I have all the holes into copper plus, oxygen band has become quarter filled. That has a bandwidth that is going to contribute to the lowering the energy of. So it is plus this. This determines what's the ground state. If the ionization energy of n-1 to n+1 is large, those are the systems which this will be greater than 0, and the system will be in the lower valence. So we are arriving at a criterion that has got nothing to do with copper oxides yet. Those systems in which the ionization energy of the lower charge is very high, they might be in a lower valence state. So what are those? We all do atomic physics at a certain point. When we are 20, and by the time we are 50, we have forgotten that. Maybe it comes back by the time you're 70. The negative charge transfer gap systems have become a quite well-known field. I'm not going to talk about nickelates, which I still don't exactly understand. The materials that I showed, they are all such materials. I don't know if I have all of them. Not in this talk, I'm sorry, but I can go back to the original slide. So here I'm plotting the total ionization energy of copper, not copper, the 3D elements. And you can see there is a peak at chromium, which is easily understandable. There is a very large peak at copper 1 plus. Why? Because copper 1 plus is 3D10. Closed shell ions have very large ionization energy. This term is going to be greater than 0. It will favor lower charge under certain conditions. So that is when I can go from here to there, and my site energy has become less than 0. I have to prove to you superconductor. That's my claim. We haven't. That's not part of this talk. But the system is now a quarter filled band of oxygen. This is closed shell. It's not taking part in transport anymore. If this is true, I should be able to explain the dimensionality change that people see experimentally. We are calculating bond orders. We showed that with doping change, there is no change in dimensionality. This is what people are hoping. I have one example of this negative charge transfer gap. These numbers are wrong, by the way. They are about 40, 50. This is my postdoc did some unit in the conversion mistake when they went from kilojoules per mole to EV. These are 44 or something. But this is one example. Why is the barium bismuth oxide only 3 plus? Well, you look up the electrode configuration, you will find out that the ionization energy of bismuth 3 plus to 4 plus is extremely large compared to its neighbors. 1 minus 1, I don't understand one system, but everything, there are about 8 or 10 negative charge transfer gap systems until now. All of them satisfy this condition that the lower charge, this chromium is actually lower charge at chromium 1 plus once you put in the crystal structure. It's exactly half filled. So if you do that, you will see these peaks at closed shell and half filled every time you have exactly half filled, not exactly, sorry, exactly half filled, putting in the crystal structure, but exactly closed shell that doesn't have anything to do with crystal structure. So what I claim is that this will have delta dT less than 0. So let's go back to the Hamiltonian and calculate the same dimensionalities, same bond orders, but now I'm changing delta dT. Delta dT goes from positive to negative. The holes have moved from copper to oxygen, and see how fast this quantity, which was flat, rises. All the other bond orders, these are the ratios. You see a distinct change in slope here. And again, just as I drew the picture H, why did you anticipate that? Because you look at the structure. The only way to have two-dimensionality and universal two-dimensional resistance is actually if you have the holes on oxygen, because they are two-dimensional. If I have all the holes on oxygen, there is far more details to it. If most of the holes on the oxygen, this is details for people who understand this field, that the TdP dominates, the oxygens will move via copper. If the bulk of the holes are on the oxygen, even with same TPP, this bond order is very small. Bond order is determined not just by Hoping integral, but also by population. Unless the population is large, this Hoping stays very small. And I'm ending my talk here that first of all, there is a universal picture towards negative charge transfer gap, and you can get to two-dimensionality. this we are still fighting by doing this. Now, I want you to think from what I told you, if that is true, I have shown this here, that the oxygen hopping will go via copper along the legs unless the oxygen population is larger than the population of copper. It will always dominate. The oxygen hopping, there are two parts, PP twice or PP directly. The PP independent of the parameter is going to lose unless the population exceeds a certain limit. So that's why you're claiming this is the only picture. So I haven't said what therefore this has to do with superconductivity. That's a separate talk. It's published. The RVB theory does become correct at quarter field. And you get the charge order, which is a paired charge order. That's a different talk. That's in this paper. You can read this faster than I can speak, even though I speak quite fast. And I'm 5 minutes before. Hey, right? 3:45, 4:45. So timing was good. Claim is this transition, in the absence of a structural distortion until 9.6 gigapascal and superconductivity is at 3.5. You cannot explain this. This is a separate talk. For those of us who are in this field, I have a far larger, something more in support. But this is for those of us who are in this field. In the whole of materials, as you dope it, the number of carriers is linear with the number of doped holes. At a certain point, it suddenly jumps. There are more recent references, and it becomes 1 plus P. I am saying this with complete faith, and trust me, there is no explanation of this. There is suddenly a large jump in carriers. Most interestingly, you see that in the number of carriers in the electron dome. It's flat and then it jumps. No explanation for this. If you think of what I'm saying, that is all given by this equation. There is going to be a point when this delta Mn no longer favors the larger charge. I2 is very large. The system has jumped over to the other side. The copper holes have all moved due to the oxygen holes. Those who are static are now moving around because there are twice as many oxygens as copper. And therefore, by working on the ladders, our claim is these two phenomena. First of all, people trying to explain them are looking at them as isolated phenomena. And the pressure-induced transition, they are all the same things. It's a signature of Venus transition, which has been seen in heavy fermions, which has been seen in organic charge transfer solids. It's the same phenomenon, coupling with the concept of negative charge transfer, for which there is a global picture. A cation with lower charge is closed shell or half-filled shell. Sorry about that. Again, okay. This is the largest set of conclusions for people in this field. Going back to the question, why has it been so difficult? Because as soon as IPC came, we must have the theory tomorrow because there is a Nobel Prize day after tomorrow. This is wrong. This thing that we are seeing, Zhang-Rai simplification, is simply wrong. You can't forget the oxygens. So we are claiming that this transition can be explained only with the Venus transition theory. Theory gives natural explanation of sudden jump in carrier densities in both electron and hole doped rare cuprates. This I haven't shown you, but we said we measure the superconducting correlations at U equals to 0, measure it at finite U, it has to increase. So we have a paper, different band fillings, triangular lattice. This increases only at one band filling. And we are claiming that in all of these cases, you can find an universal explanation of why you get this fractional charge of the anions and the closed shell. This is hard. This is half-filled. Why? Fe3 plus will give you D5. Fe3 plus will give you D5. This is a superconductor. Iridium 3 plus is D6 after you put in the crystal structure. So that's closed shell. This is half-filled. This is closed shell. This is 3 plus is closed shell because it is, to create a fourth plus, we have to take it out from, I think, 6s2. Anyway, this half filled, and you can put in other materials. Our paper gives a list of these materials. The only one I don't understand is nickelate property, but the nickelate, it will have D8 is sort of in the ferromagnetic state, you can think of it as closed shell. So the one exception that I have is nickelate, that on which we work, but the bismuth oxide, I would say that this, I said bismuth 3%, there is no bismuth 5% in 99.
D8 is also P2G complete filled and EG
And
half
two,
filled.
right. So that's why I said,
No, EG is half filled.
rare of nickelate. So Dr. Dasgupta has a paper of that. So actually, I came to know of that work last time I visited. But what I'm saying is that people are looking at these in individual papers. You can, just from atomic physics principles, and if you understand this equation, which is not even mine, I'm just adding this term. There is lower charge will be preferred even more because of this gain, because there are two oxygens per metal. That's why chromium oxide is a metal. CrO2 should not be a metal. A chromium 4 plus, chromium 3 plus makes it oxygen 1.5. And actually that one band calculation, Savatsky has a paper, they have said that the Fermi level is oxygen 2. But these are not isolated phenomena. They are all related. And I am claiming that it is also related to copper oxides. And if you were a BSc student, and somebody told you barium bismuth oxide is a superconductor, strontium ruthenate is a superconductor, lanthanum cuprate is a superconductor, and you didn't know anything, you would have said the superconductivity is due to oxygen. If you didn't know anything, then you would be right. Now, why is this important if this is right? This doesn't even touch the field of ferromagnetic superconductors, which is 50 years old. Because ferromagnetism doesn't go with superconductors, theorists have made it more and more and more and more complicated. How do I understand ferromagnetic superconductivity? Maybe there is a very easy solution. The magnetism comes from the metal. So this is the lanthanum FeO3 that Deepak was talking about. And the conductivity or superconductivity comes from oxygen. They are not going to interfere. This is TPP. This is localized magnets. There is nothing about superconductivity that is violated.
But if that is the case, will it be a triplet superconductor?
No. It will be triplet only if it goes to iron. But if
Because if irons are going to be ferromagnetic, will it not break the singlet pairs?
it depends on which Hawking dominates. I don't understand it fully. This is a conjecture. This is 30 years putting together 4 different fields. But I'm saying people are focused on the cations only. Maybe magnetism is due to cations, the superconductivity and conductivity is due to the anions. I mean, look at this is known in chemistry from 1990s. I know the Pankaj paper from 1990s. This is well known in chemistry. This is not iridium 4+. Only in 2011, physicists recognized this is iridium 3+, not 4+, because the octahedral structure iridium 3+ is D6.
By the way, doesn't core level spectra of oxygen show you whether what the
No. It is so wide and etc. No. It's very hard to interpret. However, I don't have it here. There's a guy called Jürgen Hasse in Germany. I'm forgetting his name, university, but I am in touch with him. In the electron doped materials, the transition from antiferromagnetic to superconductor occurs very subtly. And the NQR spectra disappears. I mean, NQR splitting. I had to learn NQR to find this out. It's not in this paper. The splitting between the lines is NQR is related to something called electric field gradient, which is related to the asymmetry of the electron things. It just disappears. So 5 lines, it becomes 1 line exactly at that transition. So that means that it's copper. That means the copper shell has become spherically symmetric. There's only one way, I think, it becomes spherically symmetric. Yes. There are many other experiments. You can do zinc substitution, you can do charge order. The charge order periodicity 4 has been a difficult thing. if the holes around the oxygen, the charge order periodicity is 4. I can go on and on. Yeah.
But isn't it in some excess, they see really a split peak in the age?
Sorry?
In the extra absorption spectroscopy,
Yes.
there is a strong signature of oxygen's contribution
Yes.
in terms of pre-peak
Yes.
in the oxygen age.
Yes. But that's not quantitative.
That's
That,
not quantitative.
right. That was what was used to say that the doped holes are going to oxygen.
Yes, absolutely.
That they're leading to a violent transition.
That
It's not
was not.
quantitative. That there is that. I'll tell you one other thing. The spin models. In the spin model, everybody jumped into a straight disappearance of superconductivity with zinc doping. With 3% zinc doping, it disappears. So all the spin people jumped in. Yes, copper 2 plus has spin, zinc 2 plus doesn't have spin. Of course, superconductivity disappears. Now I explain it in the electron dope case. I went to Arizona, got some experimental results saying, do the electron dope case. Superconductivity will disappear at the same concentration. Copper 1 plus is what you are creating. Zinc 2 plus is what you are doping. Both are D10. If the spin models are correct, why would zinc kill superconductivity at the same concentration? It will, because imagine there is a copper 1 plus. You have replaced it with zinc 2 plus. Right away, the surrounding oxygens have become 2 minus. Those have created the next copper 1 plus into 2 plus. Their surrounding oxygens have become 2 minus. You have created a whole area where all the coppers are 2 plus. You will get back the copper antiferromagnetic moments. That's exactly what you see next experiment. You can go through the experiments one by one, but this is a steam engine which has been going on for 30 years. I'm saying, therefore, if we go back to my second slide, that let us assume, I mean, disregard this whatever. But if I look at this, at some point we have to say, and maybe all this incremental progress is just going to lead to progress and Majorana, fermions and quantum state become all very nice things and linearity and stability, but not one of them will give superconductivity. If they did, we would have seen some indication. So I'm saying there is maybe time to change that. All right, I'm done. Thank you.
Questions, comments?
Thank you for very inspiring talk. And first, very simple question. So you plotted in order to see the crossover between 1D and 2D, you plotted the quantity B versus doping delta. And what other definition would be? Sorry, you did explain, I think, but I didn't quite follow. What was the definition of B?
What of B?
B.
The definition.
Yeah.
The expectation value of charge stress.
Uh-huh.
What's the probability of charge going from this atom to that atom?
Okay.
So we calculate copper, oxygen all along one direction. The oxygen within the thing, so that's also along the ladders. Between the ladders, the only thing that can change is oxygen. There is no change in geometry. So the copper remains small. So we calculate the inter-ladder oxygen hopping,
Okay.
which is the measure of inter-ladder coupling,
So
and all the other three.
expectation value of C dagger C.
Yes.
Yeah.
Yes.
Okay.
Ci dagger Cj
Okay.
with Ij on different sides. So the idea was that if you increase the doping, the dimensionality will increase. And it doesn't. You don't have to believe the calculations, but there is a physical picture. If you have only 0.1 or 0.2 holes in the oxygen, then the TPP becomes irrelevant. The oxygen hole will go to the copper hole moves to the oxygen. It will go through that, and therefore the intra-ladder coupling dominates. It's a population thing, it's not the hopping integral parameter.
Another question. So according to your theory, this valence transition was essential for all these cuplates and so on. So I wonder, would it be possible to see this valence transition directly by experiment?
Yes,
Yeah.
absolutely. So thank you for the question. That's a great question. And first of all, That's a great question, and I'm saying these experiments already show what we are doing, and we have a prediction for the ladder material. We haven't circulated this paper yet, but I would like to get in touch with this. I'll come to the prediction. What's happening here, if you know the literature, we are putting in more and more strontium dopings in a measuring Hall coefficient. So the Hall coefficient goes, I mean, 1 over the Hall coefficient, number of carriers, goes like this. And then you see a sudden jump, which is 1 plus P. Now, let's assume my picture is correct. You have put P holes in the oxygens, and all the copper holes jump to the oxygens. You will have exactly 1%. Let's go to the electron hole. X of the coppers are already copper 1 plus. Not all oxygen holes will go to all coppers because some of the coppers are already 1 plus. So if those oxygens move to copper plus, we'll get exactly 1 minus X. It's not just jumping. This one is plus and this is minus. That also makes sense. But the most interesting stuff is that Dr. Sahadam Gupta confirmed that for you, and maybe there are other people. When you have this change in the number of carriers, the sign of the Hall coefficient changes. It is negative here, it's positive here. That is because once the carriers are jumped, the holes are on oxygen, the carriers due to oxygen 1 minus will be positive Hall coefficient. There is a drastic change in the sign of the Hall coefficient. So what would we predict for the ladders? Where it undergoes spontaneous experiment is doable, but not everybody has that capability to do the Hall coefficient measurement under pressure. At 3.5 kilobars, we are saying that the number of carriers will jump. You will see in the ladder the same thing, except this x-axis is pressure. Not everybody has that facility, but it can be done.
Thank you very much.
What is your view on the very recent archive paper? Which, actually, it's a DMRT calculation on. They have taken SSH plus Hubbard, and they have shown that D-wave superconductivity is possible within their DMRT calculation.
Don't believe. In which material?
They have taken a model.
I don't know the paper. I'm saying right now I don't believe it, but I will discuss more after I look into the paper. But I can tell you that the barium bismuth oxide thing, some of Savarsky's collaborators are now saying is because of the oxygen breathing mode, Bi plus 3 plus O3 is semiconductor. They don't tell you what to do with the gap. If you use that, the gap becomes enormous compared to the experiment. Incidentally, I was saying, if you remember Torrance's plot, charge transfer gap ends in a D. The low charge transfer gap systems are the ones which show neutral to ionic transition. You know it, that copper oxides are very small charge transfer gap compared to other transitions. So they are very, and we know why, because this is the charge transfer gap. So the larger the ionization energy, the charge base will be closer to the inequality, and the charge transfer gap will be smaller. So what band theory is called delta dP. What I'm saying, not to be offensive, it's a fictitious quantity, because it is a superposition of all of these, and you do a calculation for the semiconductor, and then you assume it's a constant. It's not true.
Couple of things. Do you associated the valency on oxygen to be 1.5?
Which I think is a magic number. That's why barium bismuth oxide is
what
not
is
small.
the evidence of that? Because in a lot one does know where the oxygen core levels are, for instance, in O2 minus, right? So you should see some signatures of that in core levels, for instance, core level potential.
No, it's too broad. On the other hand,
but you'll see shifts, right? Peak shifts, broadening shifts, etc.
you see them, but it's not quantitative enough. I'm saying on the other hand, if you say, let's assume that you want to solve the problem, then you can say the following. Instead of making a difficult problem easier, in another way of solving a really difficult problem is to make it more difficult. Don't laugh. That's what we are doing. So, how do I make the oxide superconductivity problem more difficult? Taking the next step, if there is one BCS theory, if there is one electron photon theory for creating charge density like gaps, there is one correlated electron theory. Okay? And we have to find that. I'll show you something that most people know this. I just told you that barium bismuth oxide, bismuth is all 3+, right? Do you know the potassium concentration when it becomes superconducting? Okay, most people don't. Because why would you? You are doping it, it becomes superconducting. But if I tell you 1.5 is the magic number, if I believe it, I'm going to look for those, just like iridium telluride. Then take it from me or look it from in the literature. In a superconductor or 0.41 less than equals to x, sorry, less than x less than 0.5. Okay. Now you put in the charges, barium as 2, potassium as 1, and bismuth is fixed at 3+. Everyone can do additions and subtractions. You will find that the oxygen is 1.5. It's 1.51 to 1.54. Now you can say that's a coincidence. We can go to carbon 60 and everything else. K3C60 is quarter. So if you say this is a coincidence, then I'll bring you iridium telluride.
Could it be associated with the alkali metal atom? Because you know that potassium, for instance, has a lot of oxides, like KO2, for instance, K2O2, K2O.
That's exactly what I'm saying.
It's more with potassium than.
No, but that's exactly what I'm saying. That K2, what you are talking about, those tell us already that there are many compounds in which some of the oxygens are ones. Okay. What I'm saying is, you look at the materials systematically. There are organic charge transfer solids, 500 of them. Only 30 are superconducting. All of them are quarter field. That's a coincidence. And I'm saying that is related to this because that's a coincidence. Iridium telluride is a superconductor quarter field. You can say that's a coincidence. At some point, you have to say maybe there is something. I'm not saying this is 100%. Now, in our paper, we actually give an explanation which may not be correct, which is that if you have quarter field, then you think, okay.
Go for a colloquium and calculate.
All right.
Yeah,
I just wanted to ask you. See, even in 1, 2, 3 compounds, people are talking about peroxy system, water to mines. So, do you think that even in the 1, 2, 3 compounds also?
I'll make the 1, 2, 3. I'll put the same condition to understand the difficult problem, make it more difficult. Okay?
Tell me how you can make it.
It will take several steps. But the thing that people have forgotten, they were interested in way back, is that in yttrium barium copper oxide, you saw Plateaus and TC. Nobody talks about that. If you look at the Hall coefficient, you see a jump by a factor of 2. I'm saying if you go through this and you look at all the other parameters, and you will see that the lower plateau, I can explain with one of the layers becomes copper 1+. The higher one is the next one. I can go through stepwise. It cannot be done here. There is no explanation of the plateaus. There is no explanation. People don't even try those anymore. No explanation of why the Hall coefficient or number, if you go from 0.5 to 0.8, jumps exactly by a factor of 2. Look up Holmes paper 1987. Factor of 2. I'm not, So what I'm saying, the 65 Kelvin is 1 layer quarter field, the 90 Kelvin is 2 layer quarter field. If you say that there is copper, the coppers have got to be 1+. They don't want to be 1.2 here and 1.7.
yeah. For the interest of time, we should stop here, but we can take one question. Is there any question from online people? Any quick question? If not, let's thank these people for We break for tea, 10 minutes, and we are back.
Sorry. It's still yeah. Sorry,